last bit to look at for polynomials, and that is how do we identify multiple roots? I mean, we've got our factor theorem that allows us to find roots, but it doesn't tell us whether it's a single root, double root, triple root. So how do we deal with that? Now, it turns out that if a polynomial has a multiple root, so let's say its multiplicity is m, so it's the power of m, then its derivative will have that same root but to one less multiplicity. So if it's a triple root of a particular polynomial, it'll be a double root of its first derivative. And in fact, if you were to differentiate it again, it would be a single root of the next one there. So let's just prove that. So what we're saying is we've got this polynomial, it has a factor, x minus a to some power, times some other polynomial, but that other polynomial won't have a as a solution, because we want this to be multiplicity m. Okay, so let's differentiate it. So we're going to use our product rule, write down the first, diff the second, so q dash x, whatever that is, plus write down the second, qx, diff the first, anarchy. Bring down the power m, lower the power m minus 1, diff the inside 1, and we notice we've got a common factor of x minus a to the m minus 1. And that's what we're looking for. We want to show, hey, this is a factor of one less. Of course, we need to make sure the other factor is still a polynomial. So what have we got? We've got x minus a times q dash x plus m qx. Well, that certainly would be a polynomial. So I'll call it rx. Now, we know a is not a solution to this rx. Because if I sub in a, well, a minus a, the first part will become 0. But the second one, we specified that a was not a solution to qx. So it would not equal 0 there. So that's good. It keeps it a multiplicity m minus 1. So therefore, the derivative does have a root of x equals a to multiplicity 1 less. All right, let's apply it. So we've got this cubic, and we're told that there is a double root in there somewhere. So there's my polynomial. Rather than trying to factorise the polynomial then, what I'll do is have a look at the derivative. Because when I differentiate a cubic, I get a quadratic. Quadratics are a heck of a lot easier to factorise. So I can see my possibilities. So when I factorise that, I get two possibilities. Either negative 1/3 will be a double root, or 3 will be a double root. Now, let's think about this logically. Look at the original polynomial. Which one is it more likely to be out of the two? Why? Yeah, see, we've got a monic polynomial. So it's pretty unlikely that minus third is going to be a solution. X minus 3 squared is a factor. Leading term times leading term. Therefore, the other one's x. Constant times constant. Well, minus 3 squared is 9. 9 2s are 18, thus completing our equation. Let's solve it then. X equals minus 2, x equals 3. Now, this brings up a subtle difference between finding the roots and solving the equation. If it says solve the equation, then I have minus 2 and 3. But if it said find the roots, then my answer would be minus 2, 3, and 3. Because it has 3 roots. It's just that 2 of them were the same. Let's do a lovely HSC question. It actually came from an extension 2 HSC paper. So alpha is a root of this particular quartic. It's got nice symmetry about it. Where 2 plus b squared does not equal 4a squared. Now, I'm sure when you looked at that polynomial, you went, yeah, well, of course. All right, we're going to show that alpha can't be 0, 1, or negative 1. So that's the first part of the question. And we'll do that via the factor theorem. Well, polynomial 0, when I sub that in, I get 1. So that can't be a factor. Polynomial 1, 2a plus b plus 2. I'm not really sure whether that's 0 or not. Well, let's have a look at negative 1. And I get negative 2a plus b plus 2. Hang on a sec. Now we'll use this little fact they told us. 2 plus b squared can't equal 4a squared. Well, that means 2 plus b can't equal plus or minus 2a. Or another way of saying that, plus or minus 2a plus b plus 2 can't equal 0. Thus, polynomial 1 and polynomial negative 1 can't equal 0, so they're not roots either. So a little bit tricky there to get this other two. Our roots are, well, alpha, sorry, not our roots. One of our roots is alpha. We now have to show that the reciprocal is also a root. Okay. Again, let's use the factor theorem. Sub in 1 on alpha. I want to show this is equal to 0. Let's do an algebraic fraction on it. And let's have a look. The numerator now is 1 plus a alpha plus b alpha squared plus a alpha cubed plus alpha to the power of 4. Hang on, that's polynomial alpha. But we said alpha was a root. Therefore, polynomial alpha is 0. So 1 on alpha is also 0. So if alpha is a root, 1 on alpha will also be a root. So that's what we've just determined. Now, interestingly, this particular result, this is just as an aside, it wasn't part of the question, but this particular result, if alpha is a root, 1 on alpha will also be a root. It will always hold when you've got that palindromic situations on the coefficients. Okay, let's have a look at part C of the question. Deduce that if alpha is a multiple root, then it has to be a double root. And further, 4b has to equal 8 plus a squared. Here's my logic for the first part. If alpha is a double root, then so is 1 on alpha. Because we said, whenever alpha is a root, 1 on alpha will appear as well. So if alpha is appearing twice, because it's a double root, then 1 on alpha must appear twice. Because every time we see alpha, we see 1 on alpha. Well, that's 4 roots. But our polynomial is a quartic. And we know a quartic will have a maximum of 4 roots. So therefore it can have no more roots. So therefore, these roots can't be of multiplicity bigger than 2. Another way of saying, I suppose, is if alpha appeared 3 times, then 1 on alpha would appear 3 times. That would give me 6 roots. But I can't have 6 roots. Otherwise it would be the 0 polynomial. And it's not in this case. So we now know that alpha is a double root. They want us to show 4b is equal to 8 plus a squared. Well, because I now know it's a double root, I know it's a solution to the derivative as well. So I differentiate the polynomial. Alpha is a root of this because it's a double root. 1 on alpha must be a solution to this as well because it also is a double root. There must be a third root because it's a cubic. Well, let's just call it beta. So sum of the roots will be minus 3/4 a. Sum of the roots 2 at a time will be a half b. And sum of the roots 3 at a time will be minus 1/4 a. Now, can I play around with all this and come up with the expression that we need? If I substitute 3 into 1, I now have that alpha plus 1 on alpha is minus 1/2 a. Okay. But let's substitute it into the second expression. Now, when I substitute it in, I get 1 minus 1/4 a alpha, minus 1/4 a 1 on alpha. If I factorise just that bit, I get alpha plus 1 on alpha, which we just said is minus 1/2 a. So I can sub that in. I now have gotten rid of the alphas, so I should be able to manipulate that to get the expression. And so a little bit of playing around with the algebra, but we come up with the expression they're looking for. So 10g, 10h we'll now look at. Little note there. Okay. If a tangent to a cubic has 2 solutions only. If you know a tangent to a cubic has 2 solutions only, it must look something like that. So that will be the double root. The tangent, where the tangent meets, will be the double root. Where it cuts, it'll be the single root. And that goes back to that idea of the roots behave at the point of intersection like the power.